Commemorating the 150th anniversary of Meteorological Services Considerations on Global Warming 2, edited version. Based on 150 years of Japan Meteorological Agency observation data, 1875 to 2025, at KIS 6919. Abstract in Reference 1, the modeling of Tokyo's monthly average temperature over the past 150 years was successfully achieved. Using this, the causes of global warming will be investigated. As a secondary objective, modern history will also be studied. Introduction SDGs are widely discussed, and fossil fuels that emit CO2 are considered the enemy. However, personally, I do not fully understand the issue, and with no clear goals or results presented, being told to do what you can as an individual only leaves me confused. Nevertheless, in Japan, we have experienced severe heat and heavy rain disasters in 2023 and 2024, making global warming feel imminent. Given this situation, I aim to re-examine the causes of warming from scratch, search for ways to mitigate it, and, as a secondary goal, study history going back 150 years. Methods, Table 1, here, a table is presented showing historical temperature data and other relevant figures. The table is used to analyze the trends and factors related to global warming. Methods, continued. Figure 1, next. Figure 1 shows a 3D model of Tokyo's monthly average temperatures from 1875 to 2024, created using Reference 1. This model can be viewed from any angle and at any scale. The values show significant variation, making it difficult to grasp the overall picture. However, a detailed look at January from 1985 to 2011 reveals the appearance of green, clearly indicating warming. Methods, continued. Figure 2, next. To understand the situation from 1875 to 2024, a chronology was created based on Reference 2. Additionally, Tokyo's population was graphed using Reference 3, the average life expectancy of Japanese people using Reference 4, and energy supply trends using References 5, 6, and 7. By overlaying these with Figure 1, the causes of warming were investigated. This is shown in Figure 2. Methods, continued. Formula 1. S1 minus a pi r e squared minus a equals 4 pi r e squared sigma t e to the fourth. Where S, solar constant 1.37 times 10 to the third, watts per square meter. A, albedo. R sub e, Earth's radius, kilometers. Sigma, Stefan Boltzmann constant 5.671 times 10 to the minus eighth. Watts per square meter Kelvin to the fourth. T sub e, Earth's surface temperature, Kelvin. A, energy diffusely reflected by Earth. In this calculation, A equals 0 is assumed for Formula 1. Figure 3, an illustration showing the flow of solar energy to the Earth, considering the Earth's rotation and spherical shape. Since 1953, the annual primary energy supply by type has been published by the Agency for Natural Resources and Energy. Using the calculation method from Reference 10, the primary energy supply is substituted into the formula for evaluation. First, Formula 1 and Figure 3 are presented. From Formula 1, if the energy flowing into the Earth's surface from the Sun is S1, considering the Earth is a sphere and rotates, it can be understood that S1 S4. Next, a model is shown in Figure 4 is considered. Methods, continued. Figure 4, here, let the total primary energy supply be E, petajoule. Assume this energy is consumed within the urban planning area of Japan and convert it to watts per unit time and area, denoted as E, watts per square meter. Incidentally, the urban planning area is assumed to be 20% of Japan's land area. It is assumed that 1/3 of E is used for its intended purpose, and 2/3 are emitted as E. Also, the proportion of solar electromagnetic radiation energy absorbed by the greenhouse gas layer is set to 0.1, and for radiation from the Earth, this proportion is set to 1. Let the observed temperature be T, the temperature excluding E be T prime, the Earth's surface temperature be T sub E, and the stratospheric temperature be T sub G. Let the incoming solar energy be S1, and the reflected solar energy be S1 prime. Then, the following formulas 2, 3, and 4 hold. Methods, continued. Formula 2, sigma t to the fourth equals sigma t prime to the fourth plus E. Formula 3, 0.9s1 plus sigma t sub g to the fourth minus sigma t sub e to the fourth plus e equals 0. Formula 4, 0.1s1 minus 2.0 sigma t sub g to the fourth plus sigma t sub e to the fourth plus e equals 0. Adding formulas 3 and 4 gives sigma t sub g to the fourth equals s1. Substituting this into formula 4, 1.9s1 equals sigma t sub e to the fourth plus e. Assuming that the previously mentioned t and t sub e are approximately equal, and defining the radiation in this model as s1 prime equals sigma t to the fourth minus e divided by 1.9 equals sigma t prime to the fourth divided by 1.9. By calculating t minus t prime, the effect of e can be determined. Also, albedo what is the value of s1 prime when e equals 0, so e equals 1 minus s1 prime over s1 equals 1 minus sigma t to the fourth over s1. For e greater than 0, the corrected albedo A1 is, A1 equals 1 minus s1 prime over s1 equals 1 minus sigma t to the fourth minus e over s1. The results of these calculations are shown in Table 2. Methods, continued, Table 2, red cells, maximum values, blue cells, minimum values. Note, for 2023 and 2024, since the value of A has not been published, the 2022 value was used. The criteria in columns A and B will be explained later. Methods, continued. What can be understood from Table 2 is that the consumption of primary energy causes a change of 0.11 Kelvin to 0.99 Kelvin. However, this is much smaller than the change in annual average temperature. For example, comparing 1953 and 2004, the annual average temperatures were 287.6 Kelvin and 290.3 Kelvin, respectively, a difference of 2.7 Kelvin. In contrast, the temperature differences due to primary energy consumption were 0.11 Kelvin and 0.99 Kelvin, about 0.9 Kelvin. This indicates that, besides primary energy consumption, there are other causes of warming. These include external energy inputs, such as energy from nature and energy consumed in other regions of the Earth, which are not considered here. If so, formulas 2, 3, and 4 can be modified as follows. Formula 5, sigma t to the fourth equals sigma t prime to the fourth plus the sum, from n equals 1 to infinity, of e sub n. Formula 6. 0.9s1 plus sigma t sub g to the fourth minus, in parentheses, sigma t prime to the fourth plus the sum, from n equals 1 to infinity, of e sub n, close parentheses, equals 0. Formula 7. 0.1s1 minus 2.0 sigma t sub g to the fourth plus, in parentheses, sigma t prime to the fourth plus the sum, from n equals 1 to infinity, of e sub n, close parentheses, equals 0. In formulas 5, 6, and 7. E sub 1, primary energy supply. E sub 2, energy received from nature. E sub 3, energy input from other regions of the Earth. E sub 4, energy input from other celestial bodies in the universe. The rest is unknown. Methods, continued, Figure 5. Figure 5 is a graph of Formula 1 illustrating the relationship between albedo, A, and Earth's surface temperature, Te. From this, it can be seen that when there is no atmosphere, i.e., when it is 0, the Earth's surface temperature, Te, reaches a maximum of 278.8 Kelvin, and when at 1, it reaches a minimum of 0 Kelvin. In other words, as A dot increases, the climate becomes colder, and as A dot decreases, it becomes warmer. With the condition 0 is less than or equal to A, which is less than or equal to 1. Next, the relationship between tan A and between T and the corrected albedo A1 is shown in Figure 6. Methods, continued, Figure 6. T in a relationship diagram. The coefficient of determination is R squared equals 1, indicating a strong correlation. Annual T prime, a sub-1 relationship diagram. The coefficient of determination is also R squared equals 1, showing a strong correlation. Furthermore, the relationships between T and E sub 1, and between T prime and E sub 1, are similarly shown in Figure 7. Methods, continued, Figure 7. Annual T, E sub 1 relationship diagram. The relationship between annual temperature T and primary energy supply per unit area E sub 1 is shown. The regression equation is y equals 0.3411x plus 287.73, with a coefficient of determination R squared equals 0.5368. Annual T prime, E sub 1 relationship diagram. The relationship between annual temperature excluding E, T prime, and primary energy supply per unit area, E sub 1, is shown. The regression equation is y equals 0.1591x plus 287.73, with a coefficient of determination R squared equals 0.1989. Methods, continued, Figure 8. Annual E sub 1, a relationship diagram. The relationship between annual primary energy supply per unit area, E sub 1, and albedo, A, is shown. The regression equation is y equals negative 186.95x plus 76.99, with a coefficient of determination R squared equals 0.5359. Annual E sub 1, a sub 1 relationship diagram. The relationship between annual primary energy supply per unit area, E sub 1, and corrected albedo, a sub 1, is shown. The regression equation is y equals negative 149.68x plus 63.211 with a coefficient of determination R squared equals 0.199. Based on figures 6 to 8, the relationship among A, T, and E sub 1 is further analyzed in a 3D diagram, shown in figure 9. Results. Formula 8, T is equal to negative 118.89 multiplied by A, plus 335.61. Formula 9, T is equal to 0.3411 multiplied by E sub 1, plus 287.73. Formula 10, E sub 1 is equal to negative 186.95 multiplied by A, plus 76.99. From figure 9. 0.384 is less than or equal to A, which is less than or equal to 0.403. T in Kelvin is greater than or equal to 287.7 and less than or equal to 289.7. When A is 0.403, E sub 1 is less than or equal to 1.65 watts per square meter. When A is 0.384, E sub 1 is less than or equal to 5.20 watts per square meter. The maximum value of E1 is set at 5.20, and years exceeding this are marked with times in judgment column A. Additionally, for the range of A, years with a 0.385 are marked as warm, those within the range as appropriate, and those exceeding 0.403 as cold in judgment column B. This is because there were frequent cases where years marked times in column A were still considered appropriate in column B. Discussion. The correlation coefficients, R2, between tan E1 and between E1 and A, are approximately 0.5368 and 0.5359, respectively, indicating a significance of about 54% for both. It is difficult to judge whether these values are high or low. Additionally, the significance of the correlations between T and E1 and between E1 and A01 remains at about 20%, which is also noteworthy. When these are graphed, the result is shown in Figure 10. Furthermore, since the albedo, A, calculated from T4 is what people actually experience, this value is used in Figures 10 and 11. Discussion continued, Figure 10. As shown in Figure 10, although the primary energy supply has been decreasing since 2004, the albedo, A, has been trending toward warming. It is obvious that the amount of primary energy, E, and the emission of greenhouse gases, CO2, H2O, D2O, etc., are directly proportional, so this is contradictory. Additionally, the reasons for the shift from cooling to warming around 1990, as well as the sudden warming in 1977 to 80, cannot be explained. The cooling trend from 1953 to 1993 also cannot be explained. Therefore, I considered whether there might be another cause and arrived at the idea of nuclear tests conducted worldwide since 1945. Next, using reference 9 as material, a graph was created and compared with the previously mentioned albedo, A. There is also reference 11 regarding the relationship between nuclear tests and global warming. This is shown in Figure 11. Discussion continued, Figure 11. Since there is no data on primary energy supply before 1953, E10 was used for calculations. Between 1875 and 1945, severe air pollution was evident, likely due to the use of firewood as fuel for cooking. Aerosols were supplied in excess, increasing the albedo and causing cooling. Because of the cold and polluted air, people suffered from lung diseases, especially tuberculosis, with average life expectancies of 43 years for men and 44 years for women. During this period, life expectancy hardly changed. Additionally, since women mainly cooked at home and men were often sent to war, their life expectancies were almost the same, suggesting the high toxicity of smoke from firewood. Another reason for attributing pollution to kitchen smoke is the occurrence of food shortages from 1937 onward. The graphs show how meals were reduced from 3 times a day to 2, then 1, continuing until the end of the war. Furthermore, excessive aerosol supply due to air raids caused further cooling, and people suffered from smoke until homes equipped with LP gas stoves were rebuilt on scorched land after the war. This fact is also clearly reflected in the average life expectancy. Discussion continued. How to interpret the nuclear test graph? It is important to note that nuclear tests are shown only by frequency, and whether they were atmospheric or underground tests, the magnitude of energy is unknown. Looking at the data, there is a clear correlation. For example, in 1959, when there were 0 tests, the albedo, A, was 0.395, which matches well. The sudden warming in 1978 to 79 is, according to reference 12, likely related to the series of earthquakes at Ntaantake starting in April 1978 and the phreatic eruption on October 28, 1979. Water expands about 1,000 times when turning to gas, and at higher altitudes, lower pressure causes further expansion. This disperses aerosols and reduces albedo. Additionally, according to the same reference, Ntaantake experienced a magnitude 6.9 earthquake on September 14, 1984, causing part of the mountain to collapse and a large debris avalanche, resulting in 29 casualties. In this case, the generated particles likely became aerosols, causing cooling. The cooling in 1986 can be attributed to the Chernobyl nuclear accident on April 26. While radioactive contamination was a concern, average life expectancy continued to increase steadily from 1953 to 2010, so it seems not to have had a significant impact. The warming trend around 1990 can be attributed to the eruptions of Mt. Onzen in Nagasaki Prefecture. According to reference 13, a large amount of volcanic gas was emitted in 1973, killing about 30 cedar trees. In 1975, animal carcasses were found in the area, and high concentrations of CO2 were detected in rock fissures. After that, the dissolved carbon dioxide concentration in the Onzen hot springs rose sharply, increasing by as much as 30% in some places. Eruptions were observed on November 16, 1990, and again on April 3 and April 9, with a pyroclastic flow, Merapi type, occurring at 1608 on June 3. This disaster is presumed to have produced greenhouse gases, CO2, H2O, which lowered the albedo from 1986 to 1995. Only one eruption in this period, on June 3, 1991, is thought to have produced aerosols, and it is unlikely that these reached Tokyo, about 1,500 kilometers away. The slight temporary cooling in 1993 is explained by the La Nina phenomenon, according to reference 14. That year saw abnormal weather worldwide. From 1996 to 2007, the primary energy supply, E, was at or above its limit, so a warming trend was expected. An abnormal value for albedo, A, occurred in 2010. According to reference 15, this was the hottest summer on record at the time, and the Japan Meteorological Agency declared it a once-in-30 years abnormal weather event. There were 496 heatstroke deaths, the worst on record. Although the cause is described in reference 15, it is not convincing, so a completely new hypothesis is constructed. First, the definitions of terms are explained using Figure 12. Discussion continued, Figure 12. Aerosols necessary for cloud formation are undoubtedly airborne particles. However, at present, they have only been found in Region B, that is, as air pollutants. As an attempt in Region A, there is reference 16, but its effectiveness has not been confirmed. Discussion continued. Nevertheless, with the revision of the Air Pollution Control Act on February 12, 1997, and the enforcement of the Dioxin Special Measures Law on January 12, 2000, air pollution was reduced. However, at the same time, aerosols also decreased, lowering the albedo and promoting warming and heavy rainfall. This also provides a reasonable explanation for the recent issue of linear precipitation zones. Because there are few aerosols, water vapor condenses only at the boundary of warm and chilly air, causing heavy rain in a small area. With enough aerosols, clouds would form earlier, resulting in widespread light rain. In 2011, the Great East Japan earthquake and the Fukushima nuclear accident occurred on March 11th. The latter is still ongoing, with no end in sight. Albedo continues to trend toward warming, but this is presumed to be because the Fukushima nuclear explosion was small and supplied little aerosol. Although radioactive contamination is a concern, average life expectancy continues to increase, and no effects have been confirmed. In 2013, albedo exceeded its limit and decreased. It was a year of extreme heat and heavy rain. According to reference 17, notable natural phenomena included the M6.3 Awaji Island earthquake on April 13 and the appearance of a new island due to a submarine volcanic eruption near Nishinoshima, Ogasawara Islands, on November 20th. The second event is particularly noteworthy. It is presumed that this volcanic activity continued for a long time, supplying greenhouse gases, but since it occurred underwater, no soot was produced, and thus no aerosols were supplied. As a result, the albedo decreased. In 2017, unusually for this period, the albedo increased. The reason is presumed to be the supply of aerosols from North Korea's nuclear tests. Reference 9 cites only in the year 2017. However, additional research indicates that reference 18 also documents a nuclear test conducted in September 2016. Average life expectancy has not worsened, so radioactive contamination does not seem to be a concern. Discussion continued. In 2023, the annual average temperature was 17.6 degrees Celsius. Albedo was 0.379, the highest on record. According to reference 21, notable natural phenomena included the M6.5 earthquake in the Noto region on May 5, and multiple earthquakes caused by submarine volcanic eruptions near Torishima from October 2 to 9. Additionally, it was found that the seafloor topography near the Sofu Seamount changed by up to 451 meters in October 2022 and January 2024, with new craters forming. This is presumed to be similar to the events of 2013. On the other hand, according to the same reference, overseas events included a volcanic eruption at Mount Ulawan in Papua New Guinea on November 20, with an ash plume reaching 15,000 meters, and a magnitude 7.6 earthquake on Mindanao Island, Philippines, on December 3. On the same day, Mount Merapi in Sumatra, Indonesia, also erupted, with an ash plume likewise reaching 15,000 meters. However, due to the distance, it is thought that aerosols did not reach Japan, or only a small amount did. Finally, according to reports, 2024 is said to have experienced even greater warming than 2023. Conclusion. Tracing history from the early Meiji period in 1875 to the end of World War II in 1945, Japan experienced many wars. The author felt anger at a statement by a high-ranking official of the People's Republic of China in the news, saying, "The Japanese have no remorse," but now nods in agreement. Since the Meiji Restoration, the Japanese people have endured many hardships. These must never be repeated. Also, during this period, severe air pollution from kitchen smoke caused great harm to people. This was resolved after the war with the spread of homes equipped with LP gas stoves for cooking. Conclusion continued. There is a correlation between albedo, observed temperature, and primary energy supply, with a significance level of about 54%. Also, the calculation method shown in this paper can be mathematically extended not only to annual values but also to monthly, daily, hourly, minute, and second values. The recent extreme heat and heavy rain disasters can be reasonably inferred to be caused by a shortage of aerosols. As shown in Figure 12, aerosols that are not air pollutants have not yet been discovered in Region A, which consists of airborne particles. Early discovery is desired. Future prospects. It is speculated that the albedo could be measured by equipping weather satellites with devices that emit laser beams or radio waves and devices that measure reflections, and by installing prisms or similar devices on the ground to reflect laser beams or radio waves toward the weather satellites. Alternatively, if such equipment cannot be installed on satellites, it would also be possible to measure albedo by emitting laser beams or radio waves from ground observation points toward weather satellites and having them reflect back. If this is possible, increasing the number of measurement points and conducting frequent measurements would allow real-time tracking of albedo changes in various locations, enabling the detection of volcanic activity, CO2 and H2O emissions, and volcanic ash emissions. Additionally, there is a theory that earthquake clouds appear as a precursor to earthquakes. This could also be detected. Finally, if the albedo measured accurately by laser beams does not match the albedo calculated from the observed temperature, T, then, according to Formula 5, it would be possible to calculate N2 to 4En as well. References. 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 The end.